So far in these videos, we've been looking at using Born-Haber cycles to calculate lattice enthalpies. What we're going to do in this last video is look at the difference between experimental and theoretical values. The lattice enthalpies that will be recalculated from our Born-Haber cycles are based on experimental data, and hence are often referred to as experimental or the real values. Theoretical values can be calculated using a purely ionic model and treating the ions as point charges. As you can see from the table, there is a good agreement between the two, the Born-Haber, the real values, and the theoretical model. The theoretical model assumes the bonding is 100% ionic. You should notice in all cases the Born-Haber is more exothermic than the theoretical would predict. And for certain substances, there is a high degree of discrepancy between the two values. For example, with silver iodide, there is over 100 kilojoules per mole difference. The reason there is a difference between the theoretical and the real values is down to polarization. This is something you've come across before when we were looking at the group 2 and their thermal decomposition. So polarization is the distortion of an electron cloud of an anion by a small, highly charged cation. And a high degree of polarization leads to significant covalent characteristics. So some ionic compounds have a degree of covalency due to the polarization of the anion by the cation. So we know from our bonding that nothing is 100% ionic. This polarization explains why the Born-Haber, the real values, are always more exothermic than the theoretical. This is because the bonding is still ionic, but it has a degree of covalency on the top of it. So the bonding is stronger than you would expect it to be from a purely ionic model. Cations with a small radius and a high charge have a high polarizing power. Anions with a large radius and a high negative charge are easily polarized. Do get the difference between the polarizing and the polarized. In fact, in some cases, of very small, very highly charged positive ions, for example, aluminium 3+ ion, it is so polarizing and it distorts the electron cloud around the chloride significantly, enough so that the bonding is considered to be polar covalent rather than ionic. So this small, highly charged ion polarizes the chloride to such a degree that the bonding is no longer considered to be ionic. It is considered to be polar covalent. We can also use this idea to explain the difference between the theoretical and experimental values for something like magnesium iodide. The theoretical value assumes that the bonding is 100% ionic, but the magnesium is a small, highly charged ion. It polarizes the large anion to such a large extent that you have considerable covalent character on top of the ionic character of the magnesium iodide. Magnesium iodide is still classed as an ionic compound, but with a high degree of covalency. So as before, the theoretical assumes 100% ionic bonding. The actual values are more exothermic than that would suggest. The reason for this is that the small, highly charged magnesium ions can polarize the large iodide ions. That results in significant covalent character. And that, if you like, sits on top of the ionic bonding. So you have ionic bonding, but with a degree of covalency, making the bonding much stronger than you'd expect from a 100% ionic model. If you remember back to our bonding notes, you can have 100% covalent substances. For example, fluorine, oxygen are examples of 100% covalent, but you can't have something which is 100% ionic. You can either consider bonding in terms of the difference in the electronegativities, so you have a large difference between ionically bonded, and there's no difference between covalently bonded substances, but most things lie on some sort of continuum between the two. So there are covalent substances that have a degree of ionicness. We've now looked at it in terms of polarization. So there's no polarization here. There's a very large polarization here. But again, most things sit on the continuum somewhere between the two. We put a kind of break and we say that anything this side is going to be covalent, anything this side is going to be ionic. So, for example, hydrogen is 100% covalent because it's got two of the same, but something like HCl, where you've got a significant difference, would be a polar covalent bond. Something like aluminium oxide, Al2O3, would be classified as an ionic because the aluminium is not able to distort the smaller oxygen significantly so that you would get 100 into the covalent. But something like aluminium chloride, well, the aluminium is able to polarize the chloride to such a large extent that you get covalent bonding. Something like sodium chloride would be more ionic because the sodium is not able to polarize the chloride ion. But something like silver chloride would have a higher degree of covalency because the small silver ion is able to polarize the chloride ion. So try not to think of things as being 100% ionic or 100% covalent, but existing on this continuum between the two. Large differences in electronegativity lead to ionic bonding. No or little polarization leads to ionic bonding. If you have no difference in the electronegativities, you're going to get covalently bonded compounds or little difference. If you've got very large polarization, again, you're going to have a high degree of covalent character.